Today we're going to be demonstrating how to use force diagrams, as well as gaining a little bit more familiarity with the normal force and the frictional force by working our way through this problem. So the situation we have is a 2 kilogram block which is sitting on a 25-degree slope. We're given the coefficient of static friction between the block and the slope as 0.6, and the coefficient of kinetic friction between the block and the slope is 0.1. And we're asked, if the block is placed on the slope at rest, does it slide down the slope? To get us started, let's draw the situation in hand. We've got our 2 kilogram block sitting on our 25-degree slope. We haven't involved any forces yet. We've just set up the problem as described. Let's remember what the question is asking. We're asked if the block is initially at rest, does it slide down the slope? Now, if the block is at rest, the force we're going to be interested in is the force of static friction, which is controlled by the coefficient of static friction. So for this question, the coefficient of kinetic friction plays no role. Now that we've summarized all the information that we need in this diagram, let's get rid of the text. So we're going to start by drawing a force diagram of this box. We're doing that because we've been given information about the forces in terms of the mass and the coefficient of friction. Before we start drawing the forces, let's just remind ourselves what forces should be on this diagram. So we're looking for forces on the block. Now there are two types of forces. There are contact forces from objects actually touching the block, and then there are long-range forces. Now, the only object actually touching the block is the slope, while the only long-range force that we know of at this point is gravity. Well, gravity is the easier of the two forces to draw in, so let's start there. We know the force of gravity points straight down, and it's also one of those forces that we have a formula for. We have the magnitude of the force of gravity is mg. Okay. The slope is a little bit harder. We're actually going to break the slope up into two parts. We're going to break it up into a normal force. That is a force that's perpendicular to the surface. Let's draw that in now. Notice that we don't know how big this one is yet. We just know the direction. And we also have a friction force. And friction is going to point up the hill. We know that because in the absence of friction, this block is going to try and slide down the hill. These two surfaces, the bottom of the block and the top of the slope, are going to be in relative motion. And the job of friction is to try and stop those two surfaces being in relative motion. Okay, so we don't know the normal force and we don't know the friction force, but we do know gravity because we have the mass of the block and we have g. Okay, so this is our force diagram. These are all the possible forces on the block. There are no other long-range forces, and there's nothing else that's actually in physical contact with the block. So what we're really interested in is, will the velocity change? It started at 0, will it stay 0? That is, we're asking about the acceleration. The acceleration tells us whether or not the velocity is going to change. If the acceleration is 0, the block stays in the same place. If the acceleration is not 0, the block is going to have to change its velocity from 0 to some number, and will start sliding. How is acceleration related to the forces? Well, it's related by Newton's second law. We know F net is equal to mass times acceleration. If the acceleration is 0, F net is 0. If the acceleration is not 0, F net is not 0. So we're just trying to find whether or not the net force is 0, whether or not the block is going to stay in the place that we put it on the slope. So how do we go about finding the net force? Well, we do it by adding all of the forces on the force diagram. Now, that's not as straightforward as it seems because all these forces point in different directions. Before we actually add the forces, we have to break them into components. Once they're in components, then we can add forces that are pointing in the same direction. We're going to choose to look at forces in both the parallel and perpendicular directions. The reason for this choice, well, there's really two reasons. First, the normal force is perpendicular, the friction force is parallel. Now, the force of gravity isn't completely perpendicular or parallel, so we'll have to break this one into components. But if we'd chosen to break into vertical and horizontal components, we would have had to break the normal force and the friction force into components. The second reason that we want to break into parallel and perpendicular components is that we actually already know the acceleration in one direction. That is, we know the block isn't moving up or down off the slope. So we know the acceleration in this direction is 0. If there is any acceleration, it's going to be directed purely in the parallel direction. So we know the net force in the perpendicular direction has to be 0 as well. This will help us find our normal force. So let's break that gravitational force into components. So remember, we want to take this arrow and break it into a part that's purely perpendicular, like so, and a part that's purely in the parallel direction. These two are at right angles to one another. And so now we need to know how long is this side and how long is this side. In order to do that, let's just do some basic trig. This is a 90-degree angle. So this is 25 degrees. This is 90 degrees. The angle here, well, it has to be, the sum of all of these angles have to add up to 180 degrees. They're the inside of a triangle. So 90 degrees plus 25 degrees plus whatever this angle is have to add up to 180 degrees. That tells us this angle better be 65 degrees. Okay. With that, we know this angle here has to combine with this angle to be 90 degrees because the perpendicular direction is 90 degrees from the slope. So 65 degrees plus whatever this is have to give me 90 degrees. That tells me this angle is 25 degrees. Okay, so that's an exercise that we walk through a few times, and hopefully you're familiar with it. So let me just get rid of these lines to reduce the clutter. This angle here is 25 degrees, the same as angle as we had over here. Okay, so with that angle in hand, we can actually find these two sides. This side is the adjacent side. It's adjacent to the angle, so we get mg cosine 25 degrees. While this side is the opposite side to this angle, and we get mg sine 25 degrees. Okay. And remember, the point of these red components are to replace this blue arrow. So we shouldn't include the red and the blue. Let's just get rid of that blue arrow altogether. And then we're just going to move the components around so it's a little bit easier to see what's going on. So let's highlight all of this and move it over here. So now we've taken that gravitational force, sorry, let me move that slightly further up. Now we've taken that gravitational force and we've written it as two parts, one that's purely parallel, the parallel component, and one that's purely perpendicular. Now that the problem is in components, we can start looking for the net force in each direction. So let's do the perpendicular and the parallel parts completely separately. So just looking at the parts in the perpendicular direction, let's call this direction positive in the perpendicular direction, and this direction down here as negative. Well, from our force diagram, the net force in the perpendicular direction is N for the normal force, pointing up this way in the positive direction, minus mg cosine 25 degrees. Okay, that's from our force diagram. But we also know there's no acceleration in this direction. That tells us that the net force in that direction has to be 0. So this we got from F net equals ma. So the only way that both of these statements can be true is if the normal force is equal to mg cosine 25 degrees. Notice that there's no formula for the normal force, unlike, say, the force of gravity, which is mg. Instead, the normal force gets as big as it needs to get to stop the block from sinking through the surface. So what we had to do was we had to figure out how big that normal force was going to get by applying Newton's second law. There was no way of writing this down just from the beginning of the problem. So the normal force changes from problem to problem. Okay. But now we know what it is. In fact, we know it numerically because we've got m, we have g. So let's just put in numbers. We know the mass is 2 kilograms, g is 10 meters per second, and the cosine of 25 degrees we can work out. So we end up with a normal force of 18.13 newtons. Okay, now let's ask what happens in the parallel direction. Here, the net force is equal to, well, let's call this the positive direction and this the negative direction. So we can figure out the net force. We've got the two forces in the parallel direction are just mg sine 25 degrees pointing in the positive direction and F pointing in the negative direction. So, okay. Now, we don't know whether or not this is going to be 0. That's the question that we're trying to answer. So, frictional force, kind of like the normal force, if it's static friction, it gets as big as it needs to get to stop this block from moving, except there's a maximum value. We know that F has to be less than or equal to mu s times n. Okay. Well, we have n. N is 18.13 newtons. Mu s we also have at 0.6. So the biggest the frictional force can possibly get is, putting in values, 10.87 newtons. Okay. Now that doesn't mean that the frictional force is 10.87 newtons. It just means it's going to get as big as it needs to get to try and keep the block from moving on this surface, provided it doesn't have to get any bigger than 10.87 newtons. All right, so let's work out what's going on with the first part of this force. This we can work out numerically, mg sine 25 degrees. So we have F net in the parallel direction is equal to, well, let's put in numbers for the mass, gravity, and sine of 25 degrees. Doing that, we end up with a net force, or with a force of 8.45 newtons, okay, minus the frictional force. Now, the frictional force is going to try and make this 0, provided it doesn't have to get bigger than 10.87. And we see here that it doesn't, right? 8.45 newtons is what's needed to cancel off mg sine 25 degrees. So we're going to have F is equal to 8.45 newtons. And so F net in the parallel direction is going to be equal to 0. Okay, our block is going to stay in the same place.